Design limitations for candidate materials based on NORSOK Standard M-001, engineering constraints guiding material selection and performance. Overview of NORSOK M-001 and material selection principles, general design limitations for candidate materials. The NORSOK M-001 standard provides guidelines for material selection in offshore and onshore facilities, ensuring safety, reliability, and cost-effectiveness. It emphasizes the importance of selecting materials that can withstand harsh environmental conditions such as high pressure, corrosive media, and extreme temperatures. General considerations include compliance with international standards, life cycle cost analysis, and compatibility with design codes. Material selection must account for mechanical properties, corrosion resistance, fabrication feasibility, and maintenance requirements. These principles aim to minimize operational risks and ensure structural integrity throughout the facility's lifespan. General limitations involve environmental exposure, mechanical stress, and chemical compatibility. Materials must resist degradation from seawater, hydrocarbons, and process fluids. Limitations include susceptibility to corrosion, hydrogen embrittlement, and fatigue under cyclic loading. Designers must consider temperature extremes, pressure variations, and potential for erosion or scaling. Additionally, fabrication constraints such as welding properties, heat treatment requirements, and availability of qualified procedures influence material choice. These factors collectively determine whether a material can meet operational demands without compromising safety or performance. Design limitations for structural materials, common structural materials and their constraints. Structural materials, such as carbon steels and low-alloy steels, are widely used for load-bearing components. Limitations include vulnerability to corrosion in marine environments, requiring protective coatings or cathodic protection. Fatigue resistance is critical for components exposed to dynamic loads like waves and wind. Weldability and fracture toughness are essential to prevent brittle failure, especially in low-temperature conditions. Designers must also consider weight optimization and ease of fabrication. While structural steels offer cost advantages, their performance under severe corrosion or high-stress conditions may necessitate alternative materials or additional protective measures. Carbon steel is economical but prone to corrosion, requiring coatings and maintenance. High-strength low-alloy steels provide improved mechanical properties but may suffer from hydrogen-induced cracking. Stainless steels offer better corrosion resistance but are more expensive and can experience stress corrosion cracking in chloride-rich environments. Designers must balance cost, durability, and fabrication complexity. Structural integrity depends on selecting materials that meet fatigue, impact, and corrosion resistance requirements while remaining practical for large-scale construction. Design limitations for pressure-retaining components, material options and performance constraints. Pressure-retaining components such as vessels, piping, and valves require materials that can withstand internal pressure and corrosive fluids. Limitations include susceptibility to localized corrosion, pitting, and stress corrosion cracking. Materials must maintain strength at operating temperatures and resist creep under prolonged stress. Weldability and heat treatment are critical for ensuring joint integrity. Common choices include carbon steel for low-pressure systems and stainless steel or nickel alloys for high-pressure, corrosive environments. Designers must also consider inspection and maintenance accessibility to mitigate risks of catastrophic failure. Carbon steel is widely used for pressure vessels but requires corrosion allowances and protective linings. Stainless steels provide superior corrosion resistance but can fail under chloride-induced stress corrosion cracking. Duplex stainless steels offer a balance of strength and corrosion resistance but require careful welding practices. Nickel alloys excel in highly corrosive environments but are costly and challenging to fabricate. Each material option involves trade-offs between cost, durability, and operational reliability, making selection a critical engineering decision. Design limitations of polymeric materials, applications, and constraints in offshore facilities. Polymeric materials, including thermoplastics and elastomers, are used for seals, linings, and non-load-bearing components. Limitations include sensitivity to temperature extremes, UV degradation, and chemical incompatibility with hydrocarbons or aggressive fluids. Mechanical properties such as creep and fatigue resistance are lower compared to metals, restricting their use in high-pressure or structural applications. Designers must ensure polymers maintain integrity under operational conditions, considering factors like permeation, swelling, and aging. While polymers offer corrosion resistance and weight reduction, their performance under severe conditions requires careful specification and testing. Polymeric materials are commonly used for gaskets, insulation, and protective coatings. Their advantages include ease of installation and resistance to certain chemicals. However, limitations such as thermal degradation, fire resistance, and susceptibility to mechanical damage restrict their application in critical systems. Standards mandate rigorous qualification testing for polymers used in subsea and topside environments. Designers must evaluate long-term performance, considering exposure to seawater, pressure, and temperature fluctuations. Proper material selection ensures reliability while minimizing maintenance and replacement costs. Summary of design limitations and recommendations. Material selection under NORSOK M-001 requires balancing mechanical performance, corrosion resistance, and fabrication feasibility. Structural materials must withstand dynamic loads and environmental exposure, while pressure-retaining materials demand high strength and corrosion resistance. Polymeric materials offer specialized benefits but require careful qualification. Best practices include conducting thorough material testing, applying protective measures, and adhering to international standards. Designers should integrate lifecycle cost analysis and maintenance strategies to ensure long-term reliability and safety in offshore and onshore facilities.